Okay, so may I have your attention, please, everyone, and welcome back to ESSIC's seminar series. I'm John, the seminar coordinator. I'll be moderating the seminar with Kathy, who is our communication specialist. And today we are so happy to have Dr. Norman Grody back. And Norman is no stranger to us, and he even brought up a radiometer. So before he gets started, I think I'd like to have Ralph.
Yeah, so we're so glad to have Norm here with us. I could take the whole time to talk about everything he's accomplished, but if there was ever a microwave remote sensing Hall of Fame, he'd be the first member in it. He's legendary in the field. A couple things that jump out to mind. He was one of probably the first looking at using microwave sounding instruments to see the warm core structure of hurricanes. Only anybody ever thought you could see that. And then as we got into some of the more advanced sensors at that time, Norm developed this scattering index that was used to identify precipitation and snowfall. It's actually this picture here from, I think it's 1987. But in any case, that scattering index is still used today in one form or another. That technique. So those are just a couple things. The other thing is Norm. I learned everything I knew about microwave remote sensing from Norm, and not only I learned knowledge, but he also taught me how to have fun doing the science behind it. So I'm eternally grateful to everything I learned from Norm. And so he's still active today in remote sensing. He's building things. So pleased to have Norm start his talk. So
very good. Thank you, Ralph. Yeah. Appreciate it. I just want to start off by telling you I had a lot of experience from microwave after I finished. My PhD is originally in plasma physics and then electrical engineering. Knew nothing about microwave. Got started at NASA in 1971, and they were first launching the first microwave instruments. So I was right at the beginning. It was great to be in a new field. And I learned a few things, but really a lot of it came after I left to go to NOAA. And at NOAA, I got to work, of course, with Ralph and a few other people you may not be familiar with. There was Alan Bassett, and there was a number of others, trying to remember now. Peter Bauer, yes, well, he wasn't at NOAA, but I got to know him very well. Oh, and then I had a lot of interaction at MIT with Phil Rosenkranz, and I really want to acknowledge a lot of it. In fact, this book that I wrote, this is when I retired in 1980. Let's see, when was it again? 1985, I guess it was. No, 2005. 2005. I didn't know what to do with myself, basically, but I decided I'm going to go back to my engineering background. And I started putting things in a diary or a notebook. I started building instruments. This is one of them. And I found building the instruments taught me so much. That's something I never did at NOAA. At NOAA, I was mainly an analyst. I did a lot of algorithm development. Ralph mentioned it. Did a little calibration, not much. But then after retiring, I have to mention somebody else who's sitting right here. Boy, we had so much fun doing climate work. That's something that I never knew anything about. This is the guy who really knows that stuff. And that worked out very well for me. Well, anyway, I'm going to miss a lot of people, but I wrote a lot in this book. It's 200 pages. It talks about how to build instruments, which is what I started doing after I retired. Started building these instruments, and lo and behold, I started learning things that I never knew before. So I calibrated this. There's a method called, and I'll describe it here. It's called tipping curve, okay? Where you take the instrument, you look up its space, and what you do is you take this thing and you do it at different angles. and you measure the radiation, and from that, I'll show it to you. You can measure two things. You can calibrate it, and you can measure the atmospheric opacity or transmittance. Too many. And I'll explain it. But that was one thing I learned. And then I found something very hard to understand. I found I can do the same calibration without going in space, looking outside, just by taking a target like this with different temperatures, putting it in front of this horn, and taking the temperature difference at different temperatures. I found I can get the same calibration. I'll show you that. Anyway, that's all written in this book. It's only a 25-buck book, but man, it covers a lot. And if you want to look for it, you can. Let me go ahead and get started. I don't know how much time we're gonna have. Oh, how do I use this?
Next slide.
Oh,
Oh, no, Eric.
well, you're gonna have to help me. I'm gonna mess up. All right. So what it is, this is my second talk. The last one I gave was 4 years ago. I don't know if anybody was here. At that time, I talked about satellite work. Mentioned all the things that I measured when I was at NOAA, looking at satellites data. Some of it we still don't understand completely as far as the significance. I describe it in this book. So now I'm going into ground-based radiometer, which I never worked on until after I died. Okay, and that has to do with mention the tipping curve measurement and something else that's very complicated. And I'll explain that. I don't know if you want to get near it, but if you go near field versus far field, I'll explain what that means. And then this thing called RFI, something we never thought in the wireless beams we're going to have a problem with because we work at high frequencies. But unfortunately, now everybody else does. So we got to deal with RFI, and I'll discuss that. This I measured with this ground-based radiometer. Okay, let me get to the next one. By the way, I'll get back to some. How do I stop that? No. These three pictures I'm going to go back to. Just these things.
Yeah, just these two.
Okay. Okay, there we go. These pictures. Oh, I have them on my book cover. As Ralph mentioned, this is something we developed at NOAA. These products. These products are the satellite products of temperature, sea ice, snow cover, precipitation, and cloud liquid water. Also water vapor in there too. But this is something you could only do with a microwave instrument because of cloud problems, you know. So we put together this mosaic. But what I really want to start with is this guy. His name is Robert Dickey. He was originally the first person to ever build a radiometer like this one. And he's basically the originator of ground-based radiometry. And I'll explain some of that. But and here's the ones I built. There's an example of 3 different ones. And I'll talk about that as well. Okay, let's start off here. Okay, what's the purpose of using ground-based radiometry? Well, of course, at NOAA, we use satellites, so that's why I'm saying I don't know a lot of you don't have much background in this, so I'll bring it up. First of all, we can do controlled experiments, something you can't do very well with a satellite, obviously. And the second is more detailed measurements of things, particularly surfaces. You can actually measure the emissivity. You can have in situ measurements to go ahead and compare it with, so you can get a lot of definitive analysis of the surfaces you're measuring. And that's what this one shows. And of course, the most important that I learned is the understanding of microwave radiometers, because building an instrument, working with it, there's nothing better. I mean, yeah, you can always take data, you can massage it, you can get different kinds of elements, but it doesn't help you understand the details, particularly these 3 areas, two areas. RFI mitigation, okay? Really definitively observe it with a ground-based radiometer. You can see it from satellite, but you don't know a lot about it. except that it's there. Here you can find out what the sources are, which is what I was able to do. And then the use of high spectrum resolution using 22 gigahertz radiometer for water vapor sounding. That's something that's never been done. In other words, if you work around the water vapor line of 22 gigahertz, you have a possibility of being able to probe and measure sound. Not that great, but it's the best there is. And right now, we don't usually do that because we only use one channel usually at the water vapor line. Here you need a number of them, and I'll explain some of that with as I go on. So let's see here. All right, there's the picture I wanted to show you. There's Robert Dickey. These are his collaborators. And there's his ground-based radiometer. Now you see something here that you'll never understand, but it's true. These radiometers were built at a time when there was no such thing as an isolator. I mentioned that up on top. Now, what is an isolator? An isolator means that the radiation that this instrument sees only comes from this direction towards the antenna. But there's a problem. If you build a radiometer without an isolator, there's radiation coming in the other direction from the receiver. It's called local oscillator. That local oscillator, if you don't know how to deal with it, it's going to give you trouble. It's going to go ahead and it's going to act like a signal when it gets reflected back into the radiometer from a target. No target is perfect. And what I found is when I first built these radiometers with an isolator, and I moved this target back and forth, I would get an interference pattern because the isolator shoots out a beam and it gets reflected back and it interferes with the beam that's going forward. What Robert Dickey did, he says, I know how to deal with that. I don't have an isolator, but I got this funny looking piece of absorber, which is my reference. You know what I'll do? I'll move it back and forth very quickly. And so he took that thing, they call it a shaggy dog. And he just waved it back and forth very quickly. And when you average out the signal, because that's what a radiometer has, it has a large bandwidth and it integrates. You don't go ahead and see this interference pattern. But that is something very unique that I didn't appreciate until I started building my own. Okay, now here's the radiometers I built. They're called analog, okay? Old-fashioned, but it works. And I explained it to my last talk, all of these different components, how they work. It basically, and this is basically Dickey's design, it uses what they call a lock-in amplifier. And what it does is it locks in the signal so that you can measure the most minute amount of signal because it's referencing the output to the input through a what they call a target, a reference target, which is this noise that comes out of this resistor. So by flipping back and forth and synchronizing the switch that switches this to the switch that switches the output, you can eliminate most of the noise. And you couldn't build a radiometer without it. The other form of radiometer is called the total power, which doesn't have this, okay? And the problem with a total power is you have to calibrate very, very quickly. And that can be done in space because we always calibrate like every second, every couple of seconds. So you can do it, but you can't do it with a ground-based. So most ground-based radiometers, you still use a switch with a reference and use feedback like this in order to go ahead and minimize any fluctuations that's due to the variations in the gain of this very high gain amplifier, okay? And that's it. Here's the LNB, by the way, that's what this device is called. And if you come up later, you'll see one. And they're made up of 3 components: the amplifier, the local oscillator mixer, and another amplifier. Okay, now here's the question. Okay, if this works so great, why do we need digital? Okay, and I'm the old-fashioned type. I still like analog, but I recognize that the world is digital today. So I say to myself, why do we need a digital radiometer? Well, it has two good reasons. One of the biggest problems with these radiometers and why we have to keep launching them every few years is because there's degradation that goes on. Most of the degradation is in the detector and sometimes in the calibration system as well as the target. So if you have to deal with that because you got to launch radiometers constantly every few years, which they do with ultrasound. You can get away with that better if you use digital techniques. And the reason is you can get rid of this detector problem, okay, by taking the output here and processing it in software. You don't need to use hardware like it is here. I mean, even the lock and amplifier, everything can be done in software. And that's what I mentioned here. First, you replace the solid state detector. And the second thing is you go ahead and get rid of the filters by using digital filters. I know a little bit about digital filters. I didn't know much about the detectors, but what it amounts to, and this is very tricky. At this particular stage, you have here a signal that's very high frequency. So you need very high A to D converters to be able to go ahead and deal with these very high frequencies when you're trying to do it digitally. But if you can, then you can just do what is the way you actually compute noise, it's called Nyquist noise, simply by doing an analysis of the data and getting things like the RMS or standard deviation, which is the signal that you're actually trying to get at, which you before using a detector, you can now do it digitally. So that eliminates the solid state detector. And the other thing, of course, is the filtering, which done analog here can be done digitally, and you can get very narrow band filters digitally. Now, I don't know a lot more about the details of digital radiometers, but I will say that that's what's going on today. And I know Tiger's developed a digital radiometer. I just went downstairs to look at it. I have to spend a little more time understanding it, but it's a great concept. Now, the next slide, okay. There's the one I built, and it's similar to one that's in here. And you can see all the components laid out on that metal baseboard, metal plate. And it works. It works fine. It was an amazing thing to see how well it works, but it does work fine. I'll show you some data. Now, here's the kind of calibration that you only can do with a ground-based. I don't think you can do anything like this from a satellite. And this is the one that Dickey developed. It's called tipping curve. And it scans this in angle, as I mentioned before. You just take the instrument, you measure it as a function of angle, and I'll show you the data. And then by taking that data, you can now calibrate it. Now, it has to be clear skies. That's one thing. And you can also measure the absorption due to oxygen and water vapor at the same time. That's another parameter. Okay, let me get to the next one. Now, there's some data. Here's this radiometer up on my deck. There's an inclinometer, I think that's what they call it, measures the angle. And there's a little control in here, which you can't see, which is a voltage control which set the bias, let's say. There's my high emissivity target, which is this one right here, okay? And what you do is, again, you scan that angle, and there's the data. This is a 20.5 gigahertz radiometer. There's the zenith angle, and on top you can see the voltages, okay? And you get a curve. Okay, now that curve has a slope, and that slope is what you're going to use for calibration, because you're doing linear calibration. Okay, first of all, you do is you set the output from the radiometer to approximately 0 volts by changing the offset voltage with that little control. It's only done once. You get a temperature, you get a voltage, in this case, close to 0. And the intercept then is the temperature of the target, which is 299 Kelvin. okay? Then what you do is you take a look at this radiation transfer equation, which represents the brightness temperature that the radiometer sees, which is made up of the cosmic background radiation, which is attenuated by the transmittance raised to the secant of this angle. And then you have the attenuation, okay, but no, sorry, this is the emissivity, okay, of the temperature in the atmosphere, which is 1 minus the same transmittance value. And that's a mean temperature. Roughly, it's around 285. It varies a little bit, but it isn't that important because this is so much higher than this one here. And then what you do is you go ahead and look at this equation. You say, okay, so that's the brightness temperature. What happens when the secant of theta is 0 degrees? Well, you can see at 0 degrees, you get minus 7.5 volts. And that's not a real angle. It's an extrapolation. But it's 7.5 minus 7.5 volts. So what that means is, okay, when secant is 0 degrees, this is 0, this is 1, and therefore the brightness temperature should be the cosmic background of 2.7. So you have another point in your calibration. So therefore the slope in that equation comes 299 minus 2.7, that's the cosmic background, divided by 0, which is your offset. And 7.5 volts is what you measure. See, minus 7.5, that's why it's positive, because it's minus. And there is your slope, which is the most important thing to get. It's 39.5 Kelvin per degree per volt. That's your slope, and that's right here. And your intercept you got up there. So you got your calibration equation right there. Now the question is, how good is that? I mean, is that a real good calibration? Well, we're going to try it and compare it with another method. By the way, and I'll explain in the next slide, not only do you measure the calibration equation, but you measure the transmittance as well. Let me just show you. The transmittance that's in this formula here, of course, is made up of oxygen and water vapor, and it has an opacity alpha. Okay, now if I go ahead and substitute this calibration into this equation, which is the equation you use for measuring the opacity, out comes the opacity. Okay, because in this, that's going to be shown right here. If you took the log, I guess I used 285, but the calibrated brightness temperature we just got as a function of secant of angle, you get a straight line. I did two sets of measurements. That's why you have your dot triangle. And the slope of that is the opacity, 0.955. And that's how people measure the opacity. And that's through the oxygen and water vapor. It's mainly water vapor for that channel. So anyway, you measure two things, tipping curve. And by the way, it's because we know what the oxygen absorption is, it's fixed. You can actually reduce the total reciprocal water from the opacity. It turns out to be 22 millimeters. And that's really not hard to do. Basically, just the absorption due to water vapor in terms of water vapor. Okay, so that's that. Now let's talk about another way to measure calibration. There are three ways. There is a tipping curve I just mentioned. And then there's also a method where they use liquid nitrogen. Liquid nitrogen is tough to work with, but people like it because it's the coldest laboratory measurement you can get. And they go ahead and they look at the liquid nitrogen with the antenna to measure the lowest possible temperature that they can get easily. Okay? And then, of course, you've got your second calibration point, which is just your ambient, the warm target. That's the method that people sometimes use. But I happen to like to replace, let me see, how do I explain it here? Okay, that's the second method. The next method, of course, is just looking at space. Just taking this thing out in the field, looking at the sky, but then you've got to correct for water vapor and oxygen, assuming no clouds. So that requires a little bit of adjustment. That's not that perfect either. But the one I like is the one that doesn't use liquid nitrogen. That's the one I use in my basement. Okay, all I do is I take a target like this one, and I just vary its temperature. And I go ahead and measure the calibration that way, and this is what I'm going to show you here. Oh, there's the example. This is the 12 gigahertz unit. There's my target. I have a thermocouple in the target that tells me the temperature. And I take that target, which you can't see, it's behind this metal plate. And I put it in my freezer. And I measure a very cold temperature. It's not liquid nitrogen. And I let the temperature rise. And this is what you get. Okay, this is the target temperature, initially cool, and then goes up. All right, and you can see how it varies. Then I also took the same temperature and I take a hair dryer, I heat it up, and I let it go from a very hot temperature. That's why you got that funny looking curve. Now these are the radiometer voltage. That's the voltage coming out of the instrument itself. You can see the similarity, but when you plot it, it's even better. This is the straight line you get. Now this is varying the temperature of the target. And this is the slope that we had almost identical to what we measured with the tipping curve. 39.57. And if you look at the other one, okay. All right, what is this? 39.50. So this is let me go back here. So this is neat. I mean, you've measured your calibration. It's almost the same. It's not exactly, but it's almost the same. And I did this in a lab. Now this takes 2 hours to run because you gotta, first I set the integration time to the lowest possible because I want to be able to capture that whole rate of change. And that I think is pretty amazing. Okay, so that's using a variable time. Usually people use 2 temperatures. I pick up the whole range. So if there's any nonlinearity, you probably would see it here. Of course, you know, if you just use this, you can't be sure how well it's going to work at very cold temperatures, because that's one of the different problems. When you don't use very cold temperatures, you don't know how it's going to look when you look at space. But in this case, you can see it's almost the same. Now, this is what I'm going to talk about next, and it's a very, very difficult subject. This, I won't kid you, this is something that still has to be thought about. Okay, if I can go ahead and do this experiment, I said to myself, where I can use a warm target to go ahead and calibrate. Can I do the same thing with any target? Can I work with a non-unity emissivity target? See, this target is called EchoSorb. It's a very high emissivity target. And that has a lot of advantages. One in particular is because it's a high emissivity target, when you're looking at it, all you're doing is measuring the radiation from that target. There's no reflection. So it's like a black body. And so you don't have to worry about any kind of interference effects between the target and the instrument. And that's why it works very well. But now here's, I'm going to go over that, but let me just show you, if you haven't seen it. This is the variations in emissivity. And this is the model I use. It's an empirical model, but it works very well, at least up to 100 gigahertz. This actually assumes that you're looking at surfaces that are basically non-stratified. There's no interference pattern. You don't see any interferences in this. It's a nice smooth curve. And this is based on what I did is I took some experimental data and I fitted it to this function. Now, most surfaces act like this. It's very rare to find a surface, physical surface, that has what they call fringes or interference patterns, oscillations in the emissivity. If you do see it, there's something wrong with your data. I mean, I can only think of a few cases where you'll see that. So this is something I've used a lot. I've compared it against data. You can always fit, this is a 4-function model. You can always fit data for something like this. But what I wanted to do And this gets back a little to satellite work. I want to study these very unusual features that we see over the desert. I like the desert, by the way, because for one thing, well, it's dry. There's not a lot of clouds most of the time. And also surfaces are such that they're very, very variable. It's not like over land where you see vegetation, see water. Desert, you see all kinds of surfaces. You got limestone. You got quartz. You got, I can't think of all the different materials. I've listed a few of them here. And this is, by the way, a theoretical plot. Emissivity versus the real part of the dielectric concept. The desert materials using vertical polarization, horizontal, and at nadir. Here I'm looking at vertical. So I'm up here. And what you see here, and I mentioned this at my last talk, is this area called the empty quarter, or rubile kali, I don't know. And it's made up of quartz, lots of huge chunks of quartz. But what you find is the emissivity for that is the highest of any natural surface. It's like 0.97 and maybe even 0.98. And I saw that and said, gee, that can't be, can it? Well, if you take a look, there's another surface here called limestone. That's got the lowest brightness temperature. This is a map made up by geologists in the oil industry. And you can see all the areas. It only shows limestone. You can see how beautifully it fits the data. And this is just brightness temperature. That's not the emissivity. So I said to myself, well, let me think about this and see if it's real or not. And I was hoping to be able to measure the emissivity properties of these materials. And the one in particular I was interested in was quartz, because it has such a high brightness temperature, 285, and such basically high emissivity. You can see it calculated here. It has a dielectric constant of 3.7 if you look it up. So I decided to try and measure the properties of quartz, and I wanted to do it with my laboratory experiments, see? By the way, here's the same thing in the infrared. Okay, now what's interesting here is that quartz has the lowest emissivity, the lowest brightness in the infrared, complete opposite. Limestone has the highest brightness or highest, and this is the emissivity, they have something, but it's identical. If you look at the two pictures, you're going to have to, you look hard to see any differences, particularly in that area. So anyway, getting back, I said, okay, I want to see if I can measure the emissivity of quartz in my lab. Now here's the problem. We're all familiar with antenna patterns from microwave, and they look like that. You have side lobes, you have a main lobe, okay. Question is, what happens when you start putting things close to the antenna? Doesn't look like that anymore. It looks more like a flat distribution like that. There's a completely different model and analysis you need to use when you go near an antenna and when you go far out. And when I mean far out, I mean a distance that's greater than this, it's called 2d squared over lambda. It has to do with the diameter of the aperture, that's d, and the wavelength. And that turns out to be pretty big, particularly at short wavelengths or high frequency. So here's the problem then. How can you go ahead and use near field measurements like I'm using for my calibration? It works for my calibration target, maybe it'll work for quartz. But the problem is that there's an interaction. Anybody that's worked with computers, touchscreen devices, anything, you know when you get very close to touch the screen, things change. Very, very sensitive, because you're not dealing with the same kind of property that you're dealing in the far field. There's coupling that goes on between you and the screen, and it's called reactive coupling. Very strong coupling. In fact, the electromagnetic fields, which is represented by the electric and magnetic fields, are basically decoupled. They're not decoupled when you're going to far field. In fact, they're very highly coupled. But in the near field, they're decoupled. And dealing with that is a very complex problem. So anyway, I figured I'd give it a try. I try to use near field measurements to measure the property of quartz. And here is the problem. This is where I had a lot of help from Phil Rosenkranz. I wanted to see if I can model this near field problem with radiative transfer consideration. Okay? It's really very simple in the point of radiative transfer. You have your quartz sample sitting there. You have a piece of metal backing it, okay? So the way I did it. And there's my radiometer. And I want to see what the brightness temperature is that I'm seeing. Well, if you think about it, one thing, this radiometer that's radiating, it radiates at a temperature, roughly the temperature of the LMB or the equipment below. So you got to include that. That's called TR. That's thermal radiation. I'm not talking about electromagnetic, I'm talking about thermal. It's coming right out. Okay? And what does it do? It gets reflected by the metal. That's why you see it here as well. And you also see it getting reflected a little bit by the quartz. That's the term there, RQTR. And then you also have, of course, the emissivity of the quartz itself, which radiates at its temperature, TQ. Well, if you put all of that together, you get the brightness temperature of the radiometers, you get this equation right here. Okay? Now that equation has in it the temperature, physical temperature radiating out of the radiometer. Okay? It has in here the reflectivity of the quartz, because some of it's reflected in the quartz, and the emissivity of the quartz. Okay? And this factor F is the fractional area. You would say the fractional area of the quartz. Like when you go into a beam from a satellite, there's always a fractional amount of different surfaces. Well, that's the fraction. Well, one thing you can do with this equation, you can just drive up the temperatures and make all the temperatures the same, making it thermal equilibrium. So all the temperatures are the same. And if you do that, you get that the emissivity force is 1 minus its reflectivity. Okay? That's based on energy conservation, thermal equilibrium, whatever. And when you substitute that in, you get this final form. That's a nice form to work with because, first of all, notice, if the fractional area is 1, like it is with these targets that I completely closed, okay? And you set the emissivity to 1, because that's the emissivity of this echo source, what do you end up with? You end up with you get what a brightness temperature is equal to the surface temperature, which is what you should get. And that's why it works in calibration. All you do is you just put a high emissivity target that doesn't reflect inside, and that's how I made my calibration. So the question is, what happens if the emissivity is 1? Does this still hold? So here is what you do. You get this equation again, and if you take the slope, the change in brightness temperature divided by the change in the temperature of the quartz, out comes this thing called fractional area times the emissivity. Question is, what is the fractional area? Well, you would think it would just be the physical area of the quartz, or whatever surface, divided by the total area. That turns out not to be true. In fact, it depends on the electromagnetic field, the fields that this antenna sees, okay, from the target, divided by over the target, divided by the field it sees in the complete area of the quartz of the target itself. And that happens to be greater than the physical area. And that's the problem. Because you need to know the electric field that is seen by the radiometer. This is a diagram of what the field pattern approximately looks like through calculation. And it's basically a circular pattern. And if you don't know that, you can't compute the fractional area of the small sample. And I'll show you examples of that. Okay, so what I did is I took my piece of quartz, cracked it with an aluminum plate. The fractional area is approximately 25%. I did make the measurements of the temperature and the brightness temperature. They're both shown here. Okay? And I took the ratio, the brightness temperature, using the calibration we got before, as a function of the temperature, and I got a slope of 0.536. Now, how do I use that? Well, if I use the equation that the emissivity is the brightness temperature slope, okay, which is 0.536, and I use this fractional area of 0.25, I get an emissivity of 2.14. That's crazy. Obviously, the fractional area that I should be using is closer to 0.55 because that would give me an emissivity of 0.97. But how do I come up with that fractional area of 0.55? And that's the problem, because we need to know the field structure that's radiated when we go ahead and use this. And that's why it's not working. But I will show you some examples that I think are still interesting. Here's what I did. I took different materials. First, I took the EchoSorb, that's this material here, fully encompassing the antenna. And that's the bright, that's the bright the voltage I got from that. Then I did it for the quartz. Then I did it for an aluminum plate. Then I did it for a very small sample of EchoSorb. And they have three different distributions. By the way, this is the actual temperatures. But what I want to show you, these are slopes. Okay, got these three. Here's the EchoSorb. Here is the EchoSorb sample. I'll show you. It's a small piece. Here's this quartz, and here's the aluminum plate all by itself. So when you look at that, and these are the slopes, you get these different slopes. Here's 0.658 for the EchoSorb sample. Here's 0.585 for the quartz sample. Here's the calibration target. Look how close it is to 1, which is what it should be. It should be identically 1. Okay, and here it is for the aluminum plate, which is 0.174. So I realized by looking at those slopes that, yeah, when you completely enclose the calibration target with the, to fill the full aperture, it works perfectly. But once I start putting something that's different, well, particularly the aluminum plate, that is not the emissivity of a piece of aluminum. It should be orders of magnitude smaller. And so what I'm saying is this experiment didn't work out as I planned, but I still learned something. I learned the difficulty of using near field measurements, other than for calibration, to be able to measure the emissivity of these materials. Now I want to go to another subject. This will be the last one. Now I'm going to go into radio frequency interference. This will be a positive discussion. Okay. When we first started building these microwave instruments, we never dreamed we'd have such RFI. But the first time we took simmer measurements, we started noticing them at 6.6 gigahertz, okay? And then after that, we started seeing them at other frequencies, up to 23 gigahertz. And one of the interesting things about RFI is, well, people who developed these instruments were aware of what the Federal Communication System allotted for the frequencies to be used. And at that time, when one of the earliest, we felt safe in using 20.6 gigahertz, which is an important frequency. I'll explain it to you. Okay? But then we noticed start getting interference. So we moved it up to another frequency, 21.2, which is almost the same good as 20.6. Not exact, but good. We got interference there. Okay, lastly, for AMSU, we decided we're going to go to 23.8. And that turns out to be a safe frequency up to recently with the Wi-Fi dilemma, use of the frequencies. And now we can't even use 23.8 safely. So I wanted to see what I can measure. Okay, so here's what I did. Okay, I took my 20 gigahertz radio, it's actually 20.5. The first one, the 20.5, 20.6. And I started looking up in space. This is through a glass window. Everything I normally do is through a glass window. But anyway, those are the brightness, that's the brightness temperature variation. All of a sudden you see these jumps. It almost looks like somebody turned on something in the instrument to increase the bias. And then it went down again, then it goes up again. 12 minutes worth of RFI, 20 point. Now here's 12 gigahertz. Okay, I have another instrument that's works with 12. No interference at all. Okay, so okay, I got a little concerned first. I thought it was the instrument, and then I realized it isn't. I'll show you how here they are. Here's a 20.5. I built it up. Okay, here's the 22.2. Here's a 21.2 and a 22. There's basically two radiometers essentially in here. I use dual frequency. And I said I'll take measurements again just to see. Well, here it is. Here's my single frequency radiometers. One is a 20.5, one's a 22.2. All is at the same scale. And you can see the jumps again, 7 minutes worth of RFI. Okay. 22.2 gigahertz just shows nothing. By the way, this is noisy than that. For this particular instrument I built. But the dual frequency instrument I built, which I can show you, it has a 21.2 gigahertz and 22. 22 is much less noisy. And the 22.1.2 looks almost the same as the 20.5. And so there's that RFI that you're seeing by those two frequencies. Those two frequencies obviously are not good. I don't have a 23.8. I can't build one with that, so I can't check that. But that's what I've been seeing. The instruments work beautifully when you don't have RFI. That's this 20.5 right here. But once you have RFI, you really have problems. So I said, well, is there any way to deal with it? Well, here's how you deal with it, at least one way. Okay, if you take a look, this is looking from the ground, but you can get a similar expression if you look at the ocean surface with space, so it's not relevant. What happens is the brightness temperature you see when you go ahead and look up is the 1 minus the transmit or the absorption, and this is the mean temperature of the atmosphere. Here's your cosmic background, which is attenuated. Okay, and it turns out that that transmittance depends on the opacity through this equation, which for the water vapor channels depends on the mixing ratio, profile, and this kernel K. Okay, now this is the kernels that you would get at different frequencies. Now, if you get a flat kernel, then what you measure with this channel would be the integral of the mixing ratio, which is proportional to the total precipitate water. And that's what we use. What we say that the relationship between transmittance and total precipitate water is basically direct. But it does depend a little bit on this averaging kernel, which is shown here. And the averaging kernel for the 20.5 is pretty good. You see the blue color there. How do you get to the pointer again? Can you go?
Yeah.
Oh, all right, there you go. There's the 20. Here. Okay, there's a 20.5. And what you notice is it's pretty flat until you get to above 400 millibars, which is where most of the water vapor is. So for that particular channel, you're really measuring the total precipitate water very accurately because the kernel, the weight that it does on the mixing ratio is almost flat. Okay. Now, if you look at the 22.2, it's the complete opposite. It peaks very, very high, very low pressures, and then it flattens out. So there's a difference. And there's the 21.2, which is the other channel I use. And that one peaks a little bit high. It's not as flat. Okay. Well, what's interesting is, now this is simulations. If you were to plot one channel against the other, here's the 20.5, which is the one that's contaminated. against 22.2, which isn't contaminated, because that resides in a frequency protected region by the FCC. You get a slope that's 0.623. You see that? And you get some scatter with a standard error of 0.83, okay? So that means if you use if you had a dual frequency radiometer that had both frequencies, you can compensate a little bit for radio frequency interference, because the 20.5 gigahertz, which is affected, and the 22 isn't, you can make some adjustment. And so you can actually get rid of it. By the way, what is all that scatter that you see that leads to that? I'll show you next. It's due to two things. It's due to the water vapor distribution, which causes half of that. And the other half is due to clouds, okay? Actually, no. In this case, it's mainly due to the water vapor distribution, I should say, even though I did simulate clouds. And so this would be a filter that you can use. What it is a discriminant function. What you do is you take that equation and you subtract it, which is basically an estimate of the 20 gigahertz channel, uses the 22.2, which isn't contaminated, to come up with a discriminant function that's the difference. And if that difference, and I'll show you next, is less than -2 Kelvin, then it's RFI. If it's greater than -2, it's good. It's only due to the distribution in the water vapor profile, not RFI. And let me see if I can show you that. So that's the filter. That I call an RFI filter. It's an analog filter. Okay. Oh, wait a minute. There it is. This is the same data plotted differently. It took the difference between what I call the estimate minus the measurement. Okay? The estimate minus the measurement as a function of water vapor. I used a whole bunch of temperatures, water vapor profiles, tropical, mid-latitude. And you can see it goes above and below zero. Everything you see above zero is what I found out is the clear atmosphere. Everything that goes below zero up to -2 is through the cloudy atmosphere. So here are the effects. The clear atmosphere effects is due to water vapor profile distribution that affect the 20 gigahertz. How did I write it here? Using the 22, which is regulated by the FCC. The 20, this is the discriminant function. It's part of the difference. And as explained here, okay, varies between plus or -2 Kelvin. Okay, variations between 0 and -2 to the cloud absorption. That's what the negative is. Okay. And I use the -2 as a cutoff filter, cutoff value in my filter. In other words, anything that is going to be below this line here, it's got to be something other than atmospheric. Got to be due to RFI. But that's not perfect. I mean, you're losing a lot. For instance, you got all this variation in here. That's through the clouds. So what I'm saying is, if you added another channel, like a 31 gigahertz channel, to get rid of the cloud effect, you'd be able to bring this line all the way up to 0. And the only difference between the two, 20 and the 22 gigahertz, the 20.5 would be due to changes in the vertical distribution of water vapor, which is something that's important, and you'd like to know how to measure that. So it's possible, do something with RFI from an analog point of view, but the best way is to do it digitally. And the way it works digitally is the noise that we're talking about when we make measurements with a radiometer is called Gaussian noise. A random process, it's Gaussian, whereas the noise that we're seeing from RFI is non-Gaussian. So there was some way that you can look at the distribution rather than just the brightness temperature. So you could probably get rid of some of that. And that's what Chris Ruff did, and I referenced his paper. And furthermore, if you did that, and you did some more work on these kinds of instruments, you'd probably be able to do something about profiling water vapor by adding a 20.5 and a 22 or something like that. And that's what I'd like to think people will be thinking about doing. All you need is at least more than a single. Most of the radiometers use only a single frequency at the water vapor line. Here we're talking about more than one. And I know people have built them ground base wise, and I think it would be nice to have them on satellite. Anyway, that's my talk. Thank you.
That's a great talk. Any questions from either person or line?
Guess everybody understood it. What's that?
How much?
My radiometers?
Yeah.
$200. That's pretty cheap. That is.
Yeah,
Not
it's
a lot
like
cost,
the
but
antenna itself probably costs more. Right?
No, how much your books?
My what? Oh, my book cost.
No. But to make it, the parts only. Cost.
Oh, hours? Oh, I could build you one. It'd take me about 2 or 3 days.
Would somebody? Parts.
Well, you know, I'm not in the business. I like building things, I like measuring things, but we can talk about it.
I do have an online question. Oh, we'll take turns.
Yeah,
Can we use the sun as a hot calibration for calibrating the radiometer?
what's that?
Can we use the sun as a hot calibration
Oh
for
my
calibrating
gosh,
the
no
radiometer?
way, no, you'll burn out the radiometer for sure. Yeah, I never heard of anybody using the sun. The moon maybe, but the sun, that's a tough one. You know,
I think it
it's
is also, if you have a proper, beamers, current angle of both sun and moon will be about half degree. Even sun has very high temperature, but the solid angle ratio between the sun
yeah.
and the solid angle of antenna will be very small. So in that case, that you can actually,
Okay. but
actually you can.
pain is what I.
Yeah, like this one, the beamers of this antenna, I guess use the 15 or 16 or below 20, below 20 degree. Yeah, 20 degree, right? The 20 degree is think about the 20 degree and the solid angle of sun is only in a half degree. So its ratio is pretty.
You won't burn it out, you're saying, but I don't know what you would gain with a high, usually it's the cold targets that you want. The hot target is easy to have, it's the cold one, that's the.
The moon maybe
Yeah.
for this white beamers, the moon is maybe too low. You cannot
okay.
even.
The moon.
Okay. Yeah.
It's something to think about. Like I said, it's people, the only people I know that have really been the originators in using ground-based have been the people in Boulder, Colorado. Ed Westwater, of course, Dave Hogg, who passed away. He was the one who really built them. And I never appreciated what you can learn from a ground-based instrument till I left NOAA, retired. But it's a lot of, it's not only fun to play with, it's good experience. You really know what you're doing.
Norma, got a question, and maybe not related. I heard people say that scientists stay away from engineering, and as you have very strong background of the scientist, after done all of this, do you think what you did right now that would help what you did in the NOAA, the research work back to the past?
I stayed away from it, basically, is what I did. I stayed away from instrumentation. Now, would it have helped if I knew more about instrumentation? Not to say, because it's pleasurable to understand what you're dealing with, the instruments. But I was interested in developing algorithms using radio. Sometimes what you see with a ground base isn't what you see from space when you look at space because it's a large area. So I don't know how much it would help. I think, though, as I explained, when I get to look at certain targets, like quartz, like limestone, I would love to know more about the properties of these things. There's no way I'm going to do that from the side. I'm not going to get a field experiment over Saudi Arabia, But yet I was hoping to be able to do something like that in my lab, or something I could do, and people do. They learned a lot more. I'm trying to think of examples. I know Chris Matzner spent a lot of time learning about vegetation cover, the attenuation from leaves. I don't think you can do that just by working with space. I think you need to get more hands-on. That's why I'm a big proponent of doing experiment. We never did that at NOAA.
Our satellites use 183 for water vapor. I was just wondering, is it because you're doing in situ that you don't use 183, or can you compare and contrast 20 gigahertz and 183 gigahertz?
What? Go ahead. I guess I missed it. What were you asking?
Our satellites use 183 gigahertz for water vapor. Yeah, and you're using 22. Is that because it's a weaker line and it's better for surface?
Well, 183 area, of course, has some definition. It would be a lot like the infrared, except it would be less sensitive to clouds. I don't think you could still probe as well as you can do with the 22. And unfortunately, the problem with the 22 is we don't have as much experience. We've only had one channel. We've never really had an instrument with more than one at the 22 gigahertz water vapor line. You either had a 22 or 23.8. I think if we had more, we could learn more. I'll give you a very interesting example that I only reported in here. I wish if you haven't seen it was unbelievable. There was only one time when we had a 22 and a 19 together. That was with SSMI. They took away the 22 completely after that because they felt they just wanted to get better. What I found with the 22 and the 19, which are not that far apart, is I can very easily separate low and high emissivity over the desert. It was only then that I realized that the quartz emissivity could be so high. So usually if you go over a surface, the 22, the 19 is lower, 22 being higher, you would think the emissivity is higher at 22 than 19, but it actually reverses. If you look over the ocean, the 22 would be the higher brightness temperature than the 19. The only way you can get the 22 to be lower is if you have a very high emissivity over land. And I found that to be the case over deserts, only because I had those two channels. What I'm saying is you miss out a lot if you don't have these very close, they call it, I guess, a split window in the infrared. It's very good to have channels that are close together.
Hi, Norman here, the Mark. I have one question.
Hey, Nora.
Hi. Very interesting talk. I have one question for the prediction of the 20 gigahertz bright temperature from 22 gigahertz. Is the formula valid for all the cycle or just for nadir?
Built an instrument now that uses very small. In fact, who is it? Sanchez? How do you say it? Flavio? Oh, they built one. I thought it was in Boulder, but maybe it was in University of Amherst. I don't know. Oh, you can make these things very small. I use components I can get off the internet. These things are very small. Yeah, the only big thing is the antenna.
This would be interesting because
looking using vicarious calibration targets over the surface, it's good to know the emissivity in it. As you see, it has a lot of structure. Has a lot of structure that you can't see with the bigger
Well,
phone.
you're amazed. to
Maybe
see.
you can do your field experiment.
This runs off a battery pack. I can walk around the field with this. I don't have to.
Cool.
Okay.
Okay, we're well past the hour now, so I think we're good to wrap up. Thank you so much, Norm, for giving us this talk. Great. And thanks to everyone else for coming. We have another in-person seminar in 2 weeks from today. Look out for John's email.